and sorry, there was just a recording thing. And also now operators on this Hilbert space will correspond to observables. So we're really expected to have some kind of map that takes any smooth function, which is an observable classically, and produces some kind of operator acting on this space. And typically we expect that if it's real valued functions, we want to see self-adjoint operators acting on this Hilbert space. And then Dirac proposed a set of axioms for this process. So one of them is that it should be a linear operation, and it should take the function 1 to the identity on the Hilbert space. And then he proposed that, you know, the Poisson bracket that you have on functions on a symplectic manifold is simply taken to the commutator of the operators modulo and IH bar. And so I'll discuss that in a second about how we have to somehow modify this, because it's very hard to achieve all of these axioms in one go. But let me just try to go further with this. So these quantum observables, so in which sense are they actually observables, these operators? Well, these operators, we were going to look for eigenvalues of these operators, and I mean it in sort of a very concrete sense in this case here. You might have states of the space, which are really eigenvectors of this operator, just like this. And so I'll get to what we can observe in a second, but these are really important gadgets that you want to do when you look at quantum observables, is to understand their eigenvalues in this sense. And then the time evolution of the system is really obtained by looking at the following. You have the time derivative modified by IH bar of the states, and they are really obtained by just this time derivative by applying the Hamiltonian operator, which is the quantum operators associated to a classical Hamiltonian of the system acting on the wave function. So just solving this equation here. And if you want time evolution directly on observables, well, they are just obtained in a very similar way, but now you have a commutator with this operator H bar, gives you the time derivative of the observables. So that's the time evolution of both, states and observables on the system. Now, what is the thing about these? I don't know, so I have to press here. Okay. So if you want to sort of look at what is a typical quantum experiment you might run in a lab, well, then you would initialize your system somehow in some normalized state at the start time Ts. And then you would have a time evolution of the system that is governed by the equation we just discussed, this kind of Schrödinger type equation like this here. And now comes the measurement, which is typically the thing that you want to do at the end. If you don't measure, the quantum evolution will not really be worth anything. You have to somehow measure something after the experiment is over. What you typically want to measure is some observable f. And what you will do is that you will look at the eigenvalues. So the only thing that you can observe out of this is the eigenvalues of this observable, of this operator. And so the probability, so the only thing you can talk about is the probability of observing a given eigenvalue lambda, and that probability is simply given to you by the absolute value squared of the inner product between your end state that came out of the time evolution, and then one of these eigenstates, phi lambda, for the operator f. And so after you have observed this, what we see always is that the system then gets projected into the state phi lambda if you have observed lambda. And I think this is a really strange thing, because as far as I know, nobody understands why this measurement axiom is like this. The rest is maybe fairly easy to understand. Time evolution, you can only observe these eigenvalues and so on, but somehow we don't really understand why this collapse happens. There are many things you can say about it, but I don't think we really understand this. Anyway, let's take this in a sense from a mathematics point of view and the kind of axioms that we want to adhere to. Now, let me just show you or remind you, of course, what are the standard setups for this if we're talking about flat space R2n, which is a very simple symplectic manifold with its canonical symplectic form. Then two ways there are of realizing this whole setup is A with respect to a real polarization and B with respect to a complex one. And let me go through the real one first. So what you do is you say, okay, my Hilbert space is simply going to be L2 of Rn, where Rn is half the dimension, of course, of R2n, and you would want to select some, say, Qi's that Poisson commute. So if you select the maximum number, that will be n, so say that all the Qi's, you think of the Hilbert space as just L2 functions of those, and you have a very specific procedure for how to give the quantum operators. The Qi hats are just given by multiplication by Qi, and the Pi hats are just given by differentiation with respect to Qi modified by IH bar and a sign. And then the resulting commutation relatings out of this is the classical ones that we all know. And in fact, this way, you can also quantize, polynomials or analytic functions in PIs with coefficients in smooth functions, I should have said on Rn, simply by the following prescription. So of course, this requires some kind of ordering, right? I put all the P's to the right, and then I quantize this way. And if you apply sort of the canonical quantization procedure I've just described here to the standard, Hamiltonian, which is just kinetic energy plus potential energy, of course, you arrive at the usual Schrödinger equation in this case. And that's why, in general, I called it the Schrödinger equation. But this is the classical Schrödinger equation for a system where the energy is given by kinetic energy plus potential energy. And so there is, of course, also, as I mentioned before, a way to do this with a complex polarization. So if you identify R2n with Cn, then you have another model for the Hilbert space. Now it will be holomorphic functions on Cn, and they will have a finite L2 inner product like this. So norm, L2 inner product norm like this. Of course, you can make this into an inner product as well. And the thing is that if you do this, then the operators here will be simply Q1.
Sorry, Jan, it's not, you should put exponential factor in L2.
I agree with that. I don't know why it's not here, but it should have been here. There should be an exponentially damping factor here. This is a mistake. I don't know why it's not there. But so I agree, Max, there should be an exponential factor there. The quantum operators in this case here is simply just the Qi's go to differentiation with respect to the Zi's, and the Pi's go to multiplication. And so again, if you do this, then you get the usual standard commutation relations. And so here you see what people call the creation and the annihilation operators in this case here. But the point is that those two guys are isomorphic under a unitary equivalence, which is called a Bachmann transformation. And it is given like this. And I think also there's a mistake here. Somehow there was something happened to my exponents here. It is not exactly this kind of expression here. It's because I have been working with things where I didn't choose the appropriate trivialization of the bundle. And that's why the exponential factor is missing here. And also there's some factors missing here. But there is a very explicit expression for this Bachmann transformation, which is a unitary equivalence, and it intertwines the Qi's for this with the Qi's from the previous.
Sorry, it's again, this P hat and Q hat are not exactly these guys because they're not self-adjoint. It's complex combination of original.
Yeah, that is absolutely right. So, these are AIs and AI daggers, and there's something gone wrong with this slide here. I don't know what happened. I agree completely. The AIs are like this, and the AI daggers are like this, and then the PIs and QIs are related by usual transformations between QIs and ZIs and ZI bars. I agree. Sorry about this. This slide was kind of somehow, it suffered from the fact that I have moved from trivializations to another trivialization, I think. Anyway, we will not use it. All I can say is just that those two things can actually be used directly in the lab if they are written out correctly. And for example, here you see a system where you have actually a laser, which is here. Those lasers are pumping a couple of crystals. And then the emitted states are then squeezed in those two. And then it goes through a number of beam splitters. And what you see over here behind are some detectors. So they either do homodyne detection or they do heterodyne detection. So heterodyne detection is out here in the back. And in this way, you can actually do some quantum computing using this kind of system that I just showed you. Anyway, that's not really the main point of my talk. So let me quickly skip that. What I want to try to do now is to set up general geometric quantization for symplectic manifolds. So now I go to a general symplectic manifold, so a general phase space in physics language, and I want to introduce prequantization on that. And so there's a couple of conditions for this to work. So the quantization condition is the following, that if you look at 1 over h bar times omega, then that thing should lie in the image of h2 with integer coefficients in the image inside the h2 with real coefficients. And so if you have that condition satisfied, then there exists a complex line bundle over M with a Hermitian structure and a Hermitian connection in such a way that the curvature is exactly minus I divided by h bar times omega. And so that allows us to build some kind of complex line bundle. And now the pre-quantum Hilbert space is simply just all L2 sections of this line bundle. And there is also an operator you can associate to every function. It's called the pre-quantum operator. And it's simply given by f hat is equal to minus I h bar. And then you take the Hamiltonian vector field of f, stick it into the connection, plus f. And so you do this for all smooth functions. That makes sense for all smooth functions in this setup here. And if you just compute the commutator relations for these guys, it satisfies exactly Dirac's condition. However, this thing here results in very non-physical things. So now I don't know how to go back if there's something wrong with my machine here. But as you saw before, when it was R2n, we did not take functions of all the variables, but only of half the variables. So there is a number of problems with this. You know, it does not reproduce canonical quantization, which we know reproduces things in the lab, and so it's the right kind of thing. And also, if you go with this kind of quantization, it will contradict the Heisenberg uncertainty principle. So it really is the wrong thing to do. And what you have to do somehow in this setting here is you have to introduce what people in geometric quantization call a polarization. So you have to introduce a Lagrangian subbundle of the complexified tangent bundle. And if you do so, then what you can do is you can define the quantum Hilbert space now, which now depends on P. And it's simply the smooth sections of the line bundle in such a way that you are covariant constant along the directions which are inside P bar. In this way, it's kind of just a convention. I could have somehow just said all the x's along P, but I chose to make a little conjugation so that it fits with holomorphic sections in a second. And then if you just do this with no more information than it's just the Lagrangian subbundle of the tangent bundle, or rather the complexified tangent bundle, well, then you will hardly get any sections that are polarized in general. What you really need to do is assume that P is integrable, okay? So integrable means that if you have two sections of P and you take their Lie bracket, right, of vector fields, this should then be inside P again. And so if, that's what I say here, if you don't have this condition, you're likely to get no polarized sections. But on the other hand, if you imply that, or if you assume this, then you're likely to get quite a few sections, depending on what kind of nature P has. And let me try to look at two different ones. Let's look at the case where P is equal to P bar. There's a natural conjugation, right, coming from the last C factor here. And so if P has this property here, we call P real. And that's very natural because in that case, there actually exists a Lagrangian subbundle of the real tangent bundle in such a way that P is just a complexification of it. And so in that case, F induces, because of integrability, a Lagrangian foliation on M. And what you're really looking at is sections that are covariant constant along the foliations. But of course, in general, this could cause some problems. You know, if you have a fibration, it's all fine. But if you don't have a fibration and the foliation has dense leaves and so on, this can become a very complicated story. You may actually end up having the same conclusion like this if you stick with smooth sections, and you will actually have to go to distributional sections and all kinds of things that I really don't want to get into here. So this could be in general bad. I'm not talking about real polarizations much in this talk, except I can mention, of course, that if you are looking at M, which is a cotangent bundle, then there is a supernatural one, which is just along the cotangent fibers. And then, of course, the Hilbert space becomes nothing but, I mean, at least the pre-Hilbert space becomes nothing like smooth functions. And then, of course, you have a Hilbert space, which is just all the L2 functions on the base. But okay, that's what I want to say about real polarizations. That's not what this talk about is about. It's really about complex polarizations. And so one thing that I can emphasize is that if you have the condition on the opposite side, namely that P bar is intersect P is 0, then P is actually equivalent to an almost complex structure. And the equivalence is simply, well, that is compatible with omega. And the equivalence simply is that you take the I eigenspace of P, and that's the correspondence between Lagrangian subspaces of the complexified tangent bundle, and then I. Because if this condition is satisfied, such a P comes from a almost complex structure, if and only if it is, the E eigenspace of that complex structure. So there's a one-to-one correspondence in this case here. Now, it turns out that in this case here, P integrable is exactly the same as I being integrable. And so if you now define the following metric, and assuming that this metric is positive definite, and that means that you're really looking at a Kähler structure in this case here, well, then you have a Riemannian metric, you have a symplectic form, and you have a complex structure, and the triple is compatible via this set equation here. So that's a Kähler manifold. And those are the ones that I want to stick with and work with for now. And so I'm going to assume that I have a Kähler manifold, and I'm going to assume that I have a pre-quantum line bundle, in which case I can look at the polarized section with respect to I, and following from the definition before, in this case here, covariant constant along P bar is exactly the same as holomorphic sections of this line bundle here. And now suppose that I have a volume form, omega, which is just the standard Liouville volume form from the symplectic form, then indeed I can consider this space here. And now there is no exponential factor, because now I'm really talking about the Hermitian inner product in the line bundle. And so if we did this for R2n, you would get an exponential factor out relative to this by understanding what is the Hermitian metric in the line bundle. But in this case here, I want to look at this particular thing here. But actually, I want to later on modify this Hermitian structure, because I claim that this is not always the right Hermitian structure to consider. But I'll get back to that in a second. Okay, so now there are sort of big problems in geometric quantization of curved phase spaces in general. Namely, how does this space that I just defined depend on P? And what would the real pre-Hilbert space structure really be on this space here that we want to consider, so that, when I somehow understand how to relate the different spaces for different P, I would also be relating them in a way that it's a unitary equivalence. And next question is, how do we quantize observables? And how is that compatible with changing P and so on? And how is that going to be compatible with the various pre-Hilbert space structures I want to consider? So in the classical view on one, I guess one would say something like that the projective unitary equivalence of this Hilbert space shouldn't depend on P. And I'm wondering whether one really should stick with this. And I want to give you some indication that I believe that that's not the right way to really think about this. I'll get back to that much more in a second. And we really don't have a good answer to two in general. I also want to tell you why I think this is the case. And we do not have a general good answer for three either. Because if you look in the standard literature on geometric quantization, they would be maybe saying something like, well, if F is compatible with the polarization, you can quantize it. But it's almost no observables that has this property, okay? So you can really not quantize general observables in this setup here. But what I want to do in this talk is to offer you new ways of looking at these problems and to actually solve them, all three together. But from now on, I want to introduce a little bit different notation. So 1 over h bar I'm going to call k. And then L1 is going to be L. And then I'm just going to look at tensor powers where k is an integer, actually, of L. So I'm only going to look at this case where I'm tensor powering this a given line bundle that corresponds to, if you like, Planck's constant 1. And then I only look at integer powers of that. And then I want to look at the holomorphic sections with respect to some complex structure, with respect to those specific h bars, and I'm going to call that HIK because it only depends on the complex structure, right? Okay, so just a few remarks now. So what I really want to do is consider what happens if I have families of complex structures. So I'm going to consider a family of Kähler polarizations. And so for me, that's just going to be some complex manifold T and a map from this T into the space of all putative complex structure tensors. So they are all endomorphisms of the tangent bundle, right? So they're smooth sections over M of endomorphisms of Tm. And I want it in such a way that whenever I pick a point in T, I get a Kähler manifold. So it's a smooth family of Kähler manifolds that I'm looking for. And so what I'm going to do is that for every point in this family, I take the corresponding complex structure. I look at the holomorphic sections of L to the K over that Kähler manifold. Of course, that's a subspace of a given specific space, namely the C-infinity sections of L to the K. And these are indexed by the points in this parameter space T.
Jørgen?
Yep.
Just a question. So, right, you're looking at H naught. Are you assuming something about higher chromology?
So you are referring to this bullet point here. For the rest of the talk, we will only consider families such that these spaces form a smooth subbundle HK of the trivial bundle here. So I will
okay. No, but I have in mind, but like there might be whatever. You're looking at H0, but there might be some H1, H2, whatever, right?
That's right.
So you don't assume them to vanish.
No, I don't assume them to vanish. I am just assuming that these H0s form a bundle.
Okay, thank you.
But one could also try to look at the super generalization of this, where you take into account all the higher cohomologies and you put in the obvious sign between them, and then you would get some kind of super bundle and so on. And maybe that behaves better because of index theory and Fredholm theory and so on. But I'm going to sort of not do that here. I'm just going to focus on the H0s, and I'm going to make this very strong assumption. Okay. And so the reason why I want to do this is because I want to try to seek to find a connection in this bundle, HK here, fibered over T. And then if I can find some connection, then I will use the parallel transport with respect to this connection to give an isomorphism between the different fibers of this bundle. And so that's the way I'm going to try to understand that, you know, I get isomorphisms of the Hilbert spaces or of the vector spaces. I haven't really discussed the Hilbert space structure yet, right? Which one I really want. But I want to try to find a connection and then use parallel transport along a curve in T to give me the isomorphism of the quantum spaces. Okay, and so there are some obvious remarks to make, namely, suppose that you do actually have a Hermitian structure on HK. Then we see, of course, that the parallel transport for all curves will be unitary if and only if the connection is Hermitian with respect to this Hermitian structure, which just means that it preserves this Hermitian structure in the following sense of satisfying this equation here for any two sections, psi1 and psi2, of the bundle HK over T. And another trivial remark is that the parallel transport will be projectively independent of the choice of the homotopy class of the path from sigma 0 to sigma 1, if and only if the connection is projectively flat. And projectively flat means that its curvature is a two-form on T tends to the identity. And of course, if this two-form is 0, you can say totally independent and the connection will be flat. All right. And then furthermore, suppose that I have some symmetry group in the situation. So suppose I have some gamma, which is a subgroup of the automorphism group of the line bundle that preserves the Hermitian structure and the connection, which of course then projects to the symplectomorphisms of M. If I have such a gamma, and if I further have that gamma acts on T, and that the map I is gamma equivariant, then I can make the following remark. The projective flatness on the 2 up here implies that we will have a projective action of a pi1 extension of gamma on the covariant constant sections of the bundle. The projectively covariant constant sections, or the actual covariant constant sections if we have flatness. And further, if we have a Hermitian structure under 1, then this will be a unitary representation of this central extension of pi1 of T of gamma. So these kind of very general remarks that I can make here. Okay, so now let's study what are really the conditions for us to be able to build such a connection in this bundle, in this completely general setting here. And so the idea that we want to try to do is we want to say, okay, let's have this family of complex structures. And let's have a vector field on T. And let's look at a point in T also. And what I'm going to do is I'm going to differentiate this map I with respect to the vector field V, and then look at it at some point in the parameter space. So of course, since this is a vector space, when I differentiate, I end up in the same vector space. But if I differentiate the fact that I squares to minus the identity, I will see that the derivative of I anti-commutes with I. And that means that when I look at the way I decomposes the complexified tangent bundle into the holomorphic and the anti-holomorphic part, I see that this guy will be, skew symmetric with respect to this decomposition. In other words, it maps from the bar thing to the without the bar, and likewise without the bar to the bar. So that means that the derivative actually decomposes into these two pieces, which are in direct sum. Okay, good. And so now let's assume that T is a complex manifold. So then I can ask a further requirement of this family I. I namely say that I is holomorphic if and only if I have the following property. Suppose I take my vector field and I split it into a holomorphic part and an anti-holomorphic part like this, which I call V prime and V double prime. And then I require that if I differentiate I with respect to V prime, I get exactly this part that I identified up here of the derivative. And likewise for V double prime, I will get the other part, namely this one. And if that holds, I call it a holomorphic family. So this turns out to actually be completely equivalent to being able to build a complex structure on T. Oops, sorry. I don't know how to go back. Oh, there we go. So on T cross M in such a way that the projection from T cross M to T is holomorphic map. So I just wrote out explicitly in terms of tensors what it means that this family is holomorphic here. Okay. Very good. So now the situation we have is that we have a trivial bundle over T, which is just the one where we cross with all the smooth sections. And we are assuming we have a subbundle inside that. And now what we would like to do is, first of all, consider the trivial connection in this trivial bundle here. And then we would like to modify this trivial connection by a one form with values in the endomorphisms of this trivial bundle. Get a new connection, this nabla hat. And the whole idea is that this new connection should have the property that it preserves this subbundle. So we'd like to find modifications of the trivial connection such that this thing preserves the subbundle of holomorphic sections. And of course, since the family, if the family is totally trivial so that it just gives you back the same complex structure each time, you don't need any modification. You could just take the trivial connection. But of course, in general families, the space of holomorphic sections will vary, and so I cannot use the trivial connection. I really must find some modification U here so that it preserves the subbundles. And the ones that I want to look after is I would like to build U by differential operators. So I will look at U's which are of the form. So if I evaluate it on a vector field and look at it at some point over T, then it should be a differential operator on M acting of sections of L to the K, which would then provide me a specific endomorphism. Okay, so let's try to see if we can, yeah. Was there a question?
No, I don't think so.
No. Okay, sorry. We go on. So now let's do the following. We want to try to understand what is the condition on U for this connection to preserve HK. And so there is a little elementary lemma that one can prove. Nigel Hitchen was the first to actually prove this, but it's a one-line or two-line proof. You just look at what are the conditions for this connection here, which is the trivial connection plus U, to preserve this subspace of holomorphic things. And you find that it is exactly this equation here that has to be satisfied. So you look at any smooth section over T of HK, and then you pick a vector field V along T, and you pick a point in T, and then you look at the 1,0 part at sigma, you apply that to the section restricted to sigma, then you contract with this derivative of I, And that has to be equal to applying u of v to the section at sigma, and then applying the d bar operator in the bundle, in the line bundle to it. And that equation is simply just obtained by taking the equation that for defining the subbundle, that is lambda 0, 1 applied to the section is 0, and then you just differentiate everything with respect to v, and you will arrive exactly at this equation here. And now one thing we can observe is that if you look in the anti-holomorphic directions in T, well, then this guy here has the wrong type to be contracted with this guy. It is simply of the opposite tensor type. It is namely, its tangent space is along T bar. So therefore, when you contract with this guy here, which is in the 1, 0 direction, you will get 0. So that's what it says here. So in other words, in the anti-holomorphic directions on T, you can just take the trivial U. And so in other words, if you take the trivial connection and the 0, 1 part of it, it will actually induce a holomorphic structure in this bundle of holomorphic sections. So that's maybe not so surprising. Of course, I've taken a holomorphic family, so this bundle of H zeros will actually have a natural holomorphic structure. That's all that's being said here. But the other direction is the interesting part. How do we solve that? So one thing one can look at is a little technical detail, is that you can look at, you can ask that this connection preserves holomorphicity locally. And all that means is just that now I constrain it to say, well, you know, it will preserve holomorphicity over an open U if you have a section here, which is just a section over U, such that it actually is holomorphic, and then you require that still this U here has this property that it still satisfies this equation here. And such a thing is possible because we have U of V at sigma is actually a differential operator. So it's local, it can be restricted to open subsets of M. So you can make sense of this requirement here when you have that alpha is given by a differential operator. So if you do that, you get some stronger conclusions. So I can just look at this for a second here. So you know, if you have two connections with two different U's, and you have the property that these UIs are second-order differential operators along M, and they both preserve holomorphicity locally, then it's actually a conclusion that their second-order symbols will have to be the same. And it's a little exercise to actually do this one. You are just going to use the fact that, you know, in order to preserve holomorphicity, you will have to have this relation between the symbol of U and the derivative of the complex structure. So it's not a very hard lemma to prove, but it has a nice corollary. Namely, if you look at the space of second order such operators, which preserves holomorphicity locally, and I should also add that if there exist any of those, okay, then they will form an affine space on forms on T with values in holomorphic vector fields on M sigma plus holomorphic functions on M sigma. And you know, some very sort of special case could be, suppose M is compact. In that case, you will have that there's only the constant holomorphic functions, right? And then if you further assume that there are no holomorphic vector fields, so the Kähler manifold doesn't have any infinitesimal automorphisms, then all the second order operators will projectively agree. So it actually will be a unique operator that satisfies this if it exists. Okay. So that's what you gain out of having locality. So you get a strong constraint. Okay, now recall that there is a natural holomorphic vector bundle structure on this bundle, right? So what I might do is actually say, okay, well, somebody is going to come and tell me that there is a Hermitian structure in this bundle that I prefer. And maybe that one might even be of the following form. It is the standard L2 inner product, except I have modified it by some exponential factor here involving a smooth function from T. So just meaning I pick a smooth function on M that varies smoothly in the parameter space T. And so in fact, it turns out that any Hermitian structure is of this form by a little Toeplitz operator argument, that you can always write any Hermitian structure like this on a compact manifold, I should say. So on a compact manifold, you can always write it like this, but in general, we can consider it. Okay. And so now, you can think about the Chern connection. So there exists a unique Chern connection in this bundle in such a way that its A01 part agrees with the holomorphic structure there is in this bundle. And 2, it actually preserves this Hermitian structure you see here. So that's a way to build connections, is you God given, or whoever gives you some Hermitian structure, then you can take the Chern connection in this case. But then all of a sudden, various questions arise, right? What is the curvature of this guy here? And, can we choose the H case in such a way this is projectively fat? Or can we actually write this connection as the trivial connection plus some U? And of course we can do that. But the question is, can we find an explicit expression for that in such a way that we might be able to compute its curvature? Okay, so let me try to start approaching some of these things. But before I do that, I just want to show you a case or obstructions to actually finding flat connections that are Hermitian. So let's say that N and T are complex manifolds and that you have a holomorphic fibration. So now I just use the standard holomorphic terminology. Think of N as T times M from before, but I just need a family like this. And now I'm going to assume, say, that the dimension of the parameter space is M, and there are R dimensional, sorry, that's wrong. Say that the manifold of dimension M, this is the total space, and it's parametrized by an R-dimensional base T. Okay, so now we're going to take a holomorphic line bundle on the total space N. And now indeed, Anton, we are going to assume that all the higher cohomology groups are 0. And we're also going to assume that this map is proper. Okay, and in that case, we do get a bundle HK formed by the H0s. And what we're also going to look at is the leafwise tangent space. So that's just the kernel of d pi inside the tangent space of N. And then the Grothendieck-Riemann-Roch theorem tells us that the Chern characters of HK on the base T can be computed by taking the Chern character of L to the K, copying with the Todd class of the leafwise tangent bundle, and then pushing that forward in cohomology. And so that gives us some ways to try to compute this thing. So let's see here. So the first Chern class of the line bundle, we know what that is, right? And also what we can do is we can just decompose the Todd class of the leafwise tangent bundle into the components that lie in the various cohomologies of various degrees. And then the formula we just wrote down translates into that the Chern character of this HK bundle now is given like this. So here we can just see explicitly what is in what component. But see, now if this guy here supports a projectively flat Hermitian connection, then by Chern-Weil theory, what we know is that there will be a 1 form on the base in such a way that its Chern character is just the rank of the bundle times x of that 2 form. Right? It's the first Chern class that gives us everything because it's now a projectively flat guy. So that would just be given by this omega that I talked about earlier when I defined what projectively flatness means. And so in particular, that implies these relations here in cohomology. And those relations are far from trivial. I mean, typically, violation of these would be the obstruction for getting a projectively flat connection in this bundle. And so let's try to look at a specific example. So for example, if you look at the universal curve over the moduli space of curves, and you assume that the genus is bigger than 2, and if you then take the fiber-wise cotangent bundle, so just the cotangent bundle to all the curves, take the case tensor power over C, then by a simple Riemann-Roch vanishing theorem, you will find that the higher cohomology groups are 0. So in this case, it's just only H1, right, along the fiber. And so when you look at this, you can look at the Chern characters of the push forward of these leafwise cotangent bundles, kth power, And you can actually compute explicitly what are the Chern characters, in this case here, in terms of the kappa classes. And so, you know, the kappa classes are known to be independent classes. And so that would be a total obstruction. You know, if it wasn't, you would get these relations among the kappa classes, and they don't hold because we know they are independent for the first few, depending on the genus, right? And that grows as the genus grows bigger and bigger. So these bundles here do not support projectively flat connections. So you cannot in general hope to, and by the way, these are pre-quantum line bundles in this case here. So you cannot in general hope that this actually will give you a projectively flat identification of all of these H0s, and certainly not in general. So we should not expect to find projectively flat connections that solves this problem of independence or polarization, if that's what we believe. This is simply impossible in general. But okay, let's try to see how far can we actually go. So what we're going to do now is we're going to say, okay, let us look at a family and now look at the derivative of I and do the prime part. And then I'm going to define a symmetric, it turns out, 2 tensor, simply by the property that if I contract it with omega, I get this tensor that I get by taking the derivative. And so that defines this G uniquely, always. But now I want to say that this family I is rigid if that tensor turns out to be holomorphic. Okay, so in particular, it would be section of this bundle here. And so that is the situation where Nigel actually solved this problem first. So he looked at M compact. So the slight generalization, he actually looked at the moduli spaces of semi-stable bundles on a Riemann surface, but you can very easily from his arguments generalize it to the following way. So you let M be compact. You assume that G is holomorphic. You further assume B that there exists a lambda such that, you know, the first Chern class of M omega is actually proportional to omega, so it's lambda times omega. And second of all, you assume that, you know, 0, 1 of M sigma is equal to 0 for all sigma and T. Then Nigel proved that there is an explicit second order operator that depends on a tangent vector to T everywhere in such a way that this U here preserves locally holomorphicity. So it solves the equation we want. And then furthermore, if you have no holomorphic vector fields for any of the sigmas and T, then this guy is projectively flat and a projectively unique connection. So there's only one U that does this up to projective ambiguity. So that means just multiplication by a scalar for each value, for each sigma and T. So that solves the problem completely. In this case here, we have whatever we would like to have, nice projectively flat connection. But notice that if you actually put in here that M sigma is a Riemann surface, then you're looking at the symmetric powers of the tangent bundle, and they don't have any holomorphic sections. So you see, the only solution to these equations here in the case of this example I showed before with the universal curve would be that G is 0. And that would mean you can't vary the complex structure at all. But of course, the complex structures vary as you vary over the universal curve over the moduli space. So you see, the theorem does not apply to this case here, and so there's no contradiction with the previous stuff. And in fact, this is a very, very stringent condition on the family that it satisfies this rigidity. It turns out that the family of semi-stable bundles over Teichmuller space has this property. And so Nigel was able to apply it to that case. Okay. In fact, you don't have to somehow speculate on how U is. You can actually write down totally explicitly what U is. In the interest of time, I actually think that I want to skip discussing all of the explicit constructions there is. It's a very beautiful thing involving the Ricci potential and so on. I'll be happy to discuss it afterwards, but I think I need to move on a little bit here. So, yeah, there is a slight generalization of the theorem from before. Yeah, what you can say is that, well, let me also actually skip this part. What I want to get to, so let's focus on this second condition, namely the fact that the first Chern class should be proportional to omega. that condition can actually be removed, and the answer to this is metaplectic correction. So it can be loosened to the fact that the second Stiefel-Whitney class should vanish, i.e. the first Chern class should be even. Because if the first Chern class is even, you can actually find the square root of each of the canonical bundles. And now you can change your mind about which bundle you actually want to construct a connection in by saying, I actually want to construct it in the bundle, which I assume is a bundle now, made up of taking holomorphic sections, not of L to the K, but of L to the K tensor a square root of the canonical bundle. And so you notice that this is now inside a space which actually depends on the parameter in T, because the canonical bundle depends on the parameter, so does the square root. But it turns out it's not very hard to actually build a reference connection in this infinite dimensional bundle here, where this thing varies. You basically just use the fact that the canonical bundle is inside a trivial bundle of all, consisting of the middle dimensional wedge power of the cotangent, the complexified real cotangent bundle, and then you can use an orthogonal projection, in this case using the metric, and therefore there is a way to get a connection in this delta as sigma varies over T, and that you can use to build a reference connection. So there is a replacement for the trivial connection before, and therefore you can ask exactly the same question. Can I actually modify the reference connection by a one form, now with differential operators acting on this bundle, where I'm twisted with delta here, and such that it preserves the holomorphic sections? And so the theorem that I proved some time ago with two of my former students, Gammelgaard and Lauritsen, is that if A, so this rigidity on G, and C, which was, I remind you, this condition here, the vanishing of H01 of M sigma for all points in T, if those two are satisfied, then, and if the second Stiefel-Whitney class vanishes, then there exists a U, which is a one form on T with values in differential operators in such a way that you modify the reference connection with U, and then that resulting connection locally preserves holomorphicity. Choose in particular preserves this subbundle here, because that's just the global one, so that's taking U, the open subset, to be the whole manifold. And if, moreover, you don't have any infinitesimal automorphisms of each of these Kähler manifolds, and you have that there are no holomorphic functions on them, so no assumption about M is compact here, but just those two conditions, then this connection here is projectively unique with U given by second order differential operators. So it should be at most second order, then it's unique. And in fact, it can be written of the following form. So some specific second order operator that's constructed out of GV plus some one form. And in fact, we don't know an explicit expression for this one form in this case here, but we can show it exists. And this, with this U here, it preserves locally holomorphicity. Okay. Now, the real deal here is to try to understand how on earth do we remove this rigidity condition? Because that is a very strong condition. Actually, here I make the little remark that, again, suppose we don't have any holomorphic sections of the second symmetric power of the holomorphic tangent bundle. Well, then we can't move the complex structure at all and satisfy this condition. And that's in particular the case if you look at the universal curve. So that condition is not satisfied by the moduli space of curves and the universal curve. So we have to do something else. We need to move away from this G being holomorph. Okay, so now let me start over again by saying, okay, let's consider a general family of Kähler structures. And we are going to define a linear map from symmetric L tensors to symmetric L-1 tensors, but now tensored with the T bar star. The way that this map is built is simply you contract with the Ricci curvature and you contract with the symplectic form. So you make this combination of those two and then you contract on G. Okay, great. So that's clearly a map from here to here. And what I'm now going to do is I'm going to iteratively define, and so that was one thing. And another thing I want to do is I want to define iteratively if I have a tensor which is an L-symmetric tensor, so section of the L-symmetric product of the tangent bundle, I want to define a certain differential operator acting on this space here. And I'm going to do it iteratively in L. So if I have to do it on something of length L, what I do is first split off the first one and then apply by induction what I have defined already, minus in order to make it actually linear in the rest, so linear functions. Then I take covariant derivatives with respect to the Levi-Civita connection extended to symmetric powers acting on this, and then I stick that into that guy. There should have been an L-1 here, I'm sorry. So that iteratively defines such higher order operators acting on sections of L to the K. And so what I now want to do is the following, that I want to try to understand what happens if I apply this operator and apply d bar after that, acting on a holomorphic section of my line bundle. And so I'm going to give you just the formula in case where the curvature tensor, and so actually, sorry, I misspoke before. This is not the Ricci tensor. It's the full curvature tensor in this case here. So what I want to say is that if this curvature tensor is parallel, then I can show you very easily what the formula is. So it turns out that in this case here, what happens if you apply the d bar operator to this operator here, then you will get just d bar applied to GL minus, and then one order lower, and then you apply this map psi from before. And I just remind you that map was this map here, contraction of some IKL omega, and then the curvature tensor. Okay. So that is a really nice formula that allows you to somehow inductively understand what's going on in terms of orders. So what I will now say here is that if you want the general formula, okay, which does not involve this assumption here, then what I can say is that there actually exists a sequence of operators which are in the Helm space like this to there, such that for all symmetric tensors, if you take and apply that operator to S and then apply the d bar operator to it, you will get this formula here to hold. So the first term is just d bar of GL. Then you have IK omega contracted on one less, and then you will get corrections terms all the way down in the orders. There are specific sections of this type here that tells you exactly what are all the correction terms all the way down. Okay. Now, I can actually show you very explicitly what these A and J's are. They actually satisfy, they satisfy various recursion schemes. So you see the second guy is just the curvature tensor, and then it starts involving, iteratively applying the curvature tensor. And then if you go higher up in the J's, you start involving derivatives of the previous guys and blah, 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 blah. And so there is actually an explicit formula for solutions of all of these equations. So there are explicit formulas right here for what all of these operators are. Okay. But it simplifies if you make the assumption that nabla R is equal to 0. So I can do all of the rest of the talk for general R if you want. But in order to simplify the presentation, I'm going to assume that R is parallel, because it just simplifies a lot of the things going on here. So what I'm going to do now is I'm going to consider an F, which is a smooth function. And what I am after is to actually iteratively define symmetric L tensors, which will depend on F, and it will depend on K, the tensor power of the line bundle. And the way that I define these is that I iteratively define them by first of all saying that the zeroth guy is F. So that's a 0-dimensional tensor, so it's just the function F. Then I take and apply the nabla 0,1 to any of the given tensors I've defined already. And then I want to find the next one in such a way that it solves this equation. But you see, this equation here is algebraic on this size, because I remind you, this map was just this map here. So it's just contraction with IKL omega plus the curvature. And so you see that for large enough K, this term is dominant and omega is invertible. So I can always solve this equation here that I have here. so sorry, if k is large enough, because omega will dominate and omega is invertible, so I can solve this for large enough k. But I will now assume that they have been solved for a specific k. And so what I can now do is I can define my quantization of observables very explicitly. I will namely define them to be this formal sum here. Okay? And so let us for a moment assume that this sum here actually is convergent in the C infinity topology acting as, so it's just the operator topology where you act on each vector and you ask that the sum after action is convergent. So if you assume that that's the case, then I claim that actually this will map holomorphic sections to holomorphic sections. And so that proof is very simple, because if you take the d bar operator and apply it to this operator here, well, then you get this here. So there's some little analysis that makes sure that you can move it inside, but that was my assumption before. Now you insert the rules that I had, the iterative rules here from here. If you insert the iterative rules from here, what you will find after a bit of elimination is that you get exactly this thing here on the 1 degree lower. But that thing I made equal to 0, that's the recursive assumptions on these guys. And so this is 0.
Jørgen?
Yep.
Could you remind what are the conditions on the initial function f? Is it like anything or what?
Any smooth function at the moment.
Okay.
In such a way that, you know, I have this kind of convergence in the C infinity topology on this guy.
Yeah. Okay, okay.
But so far, there is no assumption. It's just a smooth function for now.
Okay.
So this system of equation could make sense for all smooth functions, f. And the question is whether you can solve them. But I am claiming that for large enough k, you can definitely solve them. And then you can do this construction here. And provided this has the sort of proper convergence here, you actually get that this map maps holomorphic sections to holomorphic sections. And so I claim now, well, actually, one thing I can now do is I can simply define a subspace of the smooth functions, which are called quantizable functions. And this is, by definition, the subspace for which I can solve all of the equations. And second of all, this thing gives a well-defined linear operator. Okay. And so then the question is, how big is this algebra of continuous functions? So I will try to wrap it up in about 5 minutes now, because I see I have gone at about an hour, Anton. So
I was about to ask you, and 5 minutes, that sounds great. Thank you.
5 minutes is okay? All right.
Yes.
So I think that, so what I can say is that for large enough k, actually all the analytic functions, so functions that are locally given by convergent Taylor series, are actually inside the quantizable functions. And that moreover, I get this kind of Dirac conditions. So first of all, if I take the product of the operators, then that will be for two leading order and 1 over k, just the product of the functions, and then apply the operator. But then all kinds of correction terms, infinitely many correction terms in 1 over k, but it is O of 1 over k. And if I then do the commutator, the first guy will go out, right? And so the next term is exactly as expected. It will be the Poisson bracket with an operator on. And then that's a good relation to O of 1 over k, and those are multiplied by k here.
Jørgen, what about the kernel? Does this map have a kernel, or is it like injective, or what is it?
Well, it turns out that because it has this, and it's a modification of the multiplication operator, okay? So I don't know exactly what the kernel is, but I expect that there is no kernel if you take the union over all large enough k. Or in fact, if you just take any sequence in k that goes to infinity. But
Okay.
But I'm not sure.
Okay, but for concrete k, you would expect maybe there is a kernel.
Absolutely. I think there will be a kernel in that case.
Okay, thank you.
Yeah. you know, it is, for example, suppose M is compact and this is a finite dimensional space, and then you're mapping from an infinite dimensional space just to endomorphisms of that vector space. So it has to
Right. Yeah, that's the worry. Exactly.
yeah. But if you if you take now the direct sum over a sequence of Ks that goes to infinity, my conjecture is that this is faithful.
Okay, thank you.
Yeah. So, okay, so now, I mean, somehow I'm kind of out of time, so I think I will skip the next part, because the next part really requires researchers to actually deal with this, because it turns out that, you know, this is factorially divergent, this series here. And so there's lots of stuff one has to do in order to somehow really resum this. And so I will actually skip totally over this. Unfortunately, I cannot manage to do this right now. But the point is that there is a Laplace-Borel resummation you can apply, but let me skip it just to spend 2 more minutes on actually completing this. Because what I have shown you is how to quantize functions. And now what I would like to do is also apply this actually constructions of connections. So here you can do the same thing. What you can do is you say, okay, let's assume we have such a family like here. And then actually what you can do is you start with any 0-1 form on T with values and smooth functions on M. And then you can ask that I have a recursive system of higher and higher tensors that are defined inductively. And, you know, if it wasn't for this little term here, it is exactly as I defined it for functions before. Okay, so I just evaluate each of them on a vector field, then they become just a section here. And I just ask that they satisfy exactly the same equation, except I modify to the derivative of the complex structure for L equals to 2. And so if I do this, then what I will end up with, you know, is actually a UKA, which is now an infinite order differential operator, because it's given like this to me. And now that the claim is that this guy formally solves this equation here. So you see, it solves exactly the equation so that you can define a hitching connection in this bundle here by using these operators here, provided this one here is convergent again in the same way. And so this way you can define in the same way a set of smooth forms with the on T with values and functions with the property that this, you know, whole series is convergent again and gives you a well-defined operator acting here. And in that case, this AT will parameterize hitching connections in this bundle here. And now there's no assumptions on G, because notice that the equations, the equations are exactly measuring the failure to be holomorphic at the second level, because that's this one for L equals to 3. And so before you had that this one would be generating a holomorphic section, so the whole process iteration stops at level 3, or actually stops at L equals to 2, because this is 0, so all the rest will be 0. But now in general, it will keep going up there in orders and orders and orders. But if you go to infinity this way, you will get things that really preserve the bundles. And so you see this, you can now, so you have a similar thing that you can do. You can look at all of the things that are in here, and then you can ask yourself, well, suppose that I have some condition on A in terms of derivative along T, and if they vanish to third order 1 over K, or first order in 1 over K, then what happens is that this will be asymptotically flat. And if it is just a 2 form on T tensor the identity, then it will be, asymptotically projectively flat. So you will not get flatness and projectively flat, but you get asymptotically as K goes to infinity's properties. And that's kind of the best you can hope for. Okay, here's just a thing that shows what happens in the hitching case. It all truncates the second level. I saw Anton came on, so I will try to finish. There is actually a way to understand how this relates to Hermitian structures, and you can somehow get that these connections are preserving various Hermitian structures where you have asymptotic expansions of the hitching of the Hermitian structures, and then that gives a compatibility with what kind of forms you have to choose. So I know exactly which form to choose to make it compatible with a given Hermitian structure. So I really propose that there is a quantization scheme, and that quantization scheme somehow has to depend on which family of Kähler structures you want. And then you should either choose the Hermitian structure, or you should choose the connections that relate them, and then that will determine the other one. And so that, I think, is really the setup we cannot hope that the quantization independent of polarization. It highly depends on the family of polarizations we choose. So there's more said here, and I just said that in words. There's something about the action of groups also. I will skip that altogether. But I think that the main message is that the quantization will really rely on the family you consider. And the bigger symmetry group you want, the bigger T will have to be. The bigger space of observables you want, that will force T down to be smaller. And for example, if you take just a single Kähler structure, then of course you can get a lot of functions to be quantized, but you will not have much symmetry to play with. So there's a trade-off between the two. So that's my main message. Sorry, it became a little fast in the end. Thank you very much.
Well, thanks a lot. Thank you. So any questions or comments? You can either raise your electronic hand or unmute yourself or and ask your question. Alejandro.
Hello. Hi. Thank you for the very interesting talk. I have two questions. One is more heuristic. It has to do with Berry phases, because some of the ingredients that you have in the beginning when you have a parameter space and a bundle of Hilbert spaces are familiar from Berry phases. And I was wondering if in your case there would be something meaningful when you trace a loop in the space of parameters. Like physically meaningful Berry phase or something like that?
Yes, I mean, in a sense, I think that is a very interesting question, because what I'm getting here is that there is, connections, and these connections are not flat. So in many cases, they will have to have curvature, as I demonstrated in an example, right? So in general, we expect them to really have curvature. And so if you imagine that you start at some point where you have a specific Kähler structure, so you can either think complex structure or you can think metric, right? They are equivalent. So what you would be doing is doing a little loop in the space of metrics. So just to put it in a contemporary context, you are in a situation where your quantum system is experiencing a quantum wave, right? A gravitational wave runs through your experiment. Then this little loop in metrics, well, the parallel transport around this loop here should induce an endomorphism of the system. So it does not necessarily, so the system doesn't come back to itself. There is a monodromy of the system, a bit like a Berry phase. And you should be able to somehow detect this, I think, in a system. But as far as I can tell, it is of second order in H bar.
Ah, okay. Very interesting.
So it is a small effect on the system. And so you really have to measure very precisely to the second order. So the second power of H bar, right? And since H bar is minuscule, it's a huge factor, right? But it should be an effect, but I think it's of order H bar squared.
Okay, thanks. So, and the second question is about comparison to what happens with the Berezin-Toeplitz quantization. Your operators F bar, how do they compare to them? And do you know if there is a star product induced by your quantization?
So there is a star product induced by this process here. And it's given by differential operators. You can write it down explicitly to all orders, since I have all of these tensors described. So you can actually see how it is explicitly. But I don't know yet exactly how these constructions relate to Toeplitz operators.
Okay, thank you.
Yeah, you're welcome. Thank you.
Yeah, thanks a lot, Janusz.
Yes, so this geometric quantization developed in very deep and complicated theory. Your talk is an example. But going back to the origins, so this is based on the idea that there is something like quantization which should realize Poisson bracket of the classical observables in terms of commutations of quantum operators or whatever. But there are many, so this Dirac's program is, of course, it is known that it's wrong. There are many no-go theorems. We publish some of them in a few papers with Marc Gauthier, but there is one nice purely algebraic observation made in one of these old papers, namely that that no Poisson algebra of functions on the manifold can be realized as a commutator bracket in an associative algebra. So this is just algebraic no-go theorem, which says that Poisson brackets cannot be realized as commutators. Yeah, so this is no. So we have a very nice geometrical theory and deep theory, but I'm afraid we lost some relation to the quantum physics.
Well,
yeah,
I don't know what exactly you mean here, because I think this carries a close relation to quantum physics, because you see, I am not claiming that this operator here has the property that the Poisson bracket is a commutator. It is only true to 1 over k.
Okay, but do you see any quantum physics application of your result?
Well, I think I would refer to the previous question, namely, what this seems to indicate is that if you have a gravitational wave which hits your quantum system, there should be a detectable effect. Because this will curve the space so it is no longer flat. And once it is not flat, then in fact it is the more general thing that I didn't talk about, namely when Nabla of R is not 0, there is a more complicated system that kicks in. But there are correction terms that you will see, and there will be a connection that tells you how to parallel transport around the loop, and the parallel transport will not be 0. It's because the connection is not projectively flat. So even projectively, it will not be 0. It will make some endomorphism of the space, which should be detectable, but it is of the order h bar squared.
Okay, thank you.
Thanks a lot. More questions or comments? Maybe I have sort of naive question. So you mentioned compact manifolds. What about just a sphere S2, right? And then then probably everything is controllable. So your maps, what's the outcome? Of course, there are finite dimensional matrices for each value of k, and now is it known that it's injective if you sum over all k?
Yes, all of that works.
Whatever.
All of that works in this case. I can write down explicitly what the higher tensors are. Everything is very simple because it's a one-dimensional manifold complex, right? So all of these symmetric powers are simply just tensor powers of the tangent bundle in this case, which is a line bundle, and so you can write down everything quite explicitly in that case. So there is a specific recursion that you solve, and it's not easy, not complicated to do.
Okay.
And you can do the same for flat space, of course. And if you do it for flat space, you recover the standard quantization rules.
Okay, look, thanks a lot. Unfortunately, I would have to go, but I pass to Nikita the role of the chair. And thanks a lot, Jørgen, for a wonderful talk.
Thank you, Anton. Thank you for asking me.
Okay, so does anyone else have any questions for Jørgen? I think that's a no. So I think Anton left exactly at the right moment. All right. Well, in that case, let's thank the speaker one more time.
Thank you.
All right. Thank you, Jørgen.
Thanks a lot, Nikita.
All right. Bye, everyone.
Okay. See you. Bye-bye.